want to welcome you to my lecture today. Before I get started today, I got some announcement. Number one, I want to remind you that midterm one will be written on Friday, February 25. And the areas of focus, of course, is going to be chapter 0, 1, and 2. Okay, chapter 0, 1, and 2. Just like what I said the other time. There's going to be new assignment this week. I did not give assignment last week because I actually wanted to spend more time very early on the midterm practice question. And you know what? This week, we're going to finish chapter 4. When we finish chapter 4, it means we've already finished unit, the second unit in the course. And now I've edited the syllabus. I wanted to go back to the syllabus and check. I've already edited that. Okay. And I also want to tell you midterm 2, we focus on chapter 3, 4, and 5. You know, we are on chapter 4 right now. We haven't started chapter 5. So I'm just trying to tell you so that you're actually going to know the area of focus for midterm 2 as well. Okay, like I said, chapter 4 will be completed on Wednesday. And of course, there's going to be a review on the assignment, the new assignment that will be posted today on Wednesday, just like what I normally do. I want to welcome you to my lecture today. Today, we are still going to focus on additional topics in regression that I call part 2. But today, the focus is basically going to be on variable selection. You know, we find ourselves in a world that is, you know, stochastic in nature, probabilistic in nature. We live in a probabilistic space. And you know what? How do we take a decision that we are not going to regret? To take a decision that we're not going to regret, we need information. You know that? We need information. The information that we need is not readily available. We actually need to collect data set. And even when you collect your data set, the information is not readily available. You are not going to have access to that unless you actually confront your data set with an appropriate model. And here we're using statistical model. And I told you from the one, we use model to capture reality. But you know what? No matter how we try, there's going to be a loss of information. The best model will be characterized by loss of information. And because of that, we have a conclusion that model is not an exact reality. Now, we want to investigate relationship among variables. If I have a time, we're going to begin with two variables, one predictor, the other one response. We came with assumptions, okay? When we specify linear regression model, okay, that will come with assumptions, linearity, normality, constant variance, independence, and the absence of unusual observations. And of course, when we do that, we actually have a way to investigate whether the model is really doing a great job. And I'll also walk you through a situation where we actually needed more than one predictor in a model. And I walk you through what we call the multiple linear regression. And I also walk you through a situation whereby the relationship between the variable may not be a straight line. Maybe we needed to add a quadratic effect or a cubic effect. And that actually leads us to polynomial regression. And we also consider a situation whereby maybe incorporating interaction into a model, interaction time into a model, maybe it's also going to do a great job. We have a way to investigate significance of whatever variable we are actually adding into a model. And you know what? The focus today is basically going to be, do we have a way to select important variables into our model? Because situation where you have variable that is not important in your model is actually going to undermine the performance of the model. And you know what? Situation where important variable is missing in your model, then your model is not going to do a great job. And what do we want to do today? We have an established way to identify the important variables in the model. But let me tell you this. When important variables are missing in a model, instead of you to fix a model with a lot of variables, if you end up fixing model with few numbers of variables, maybe because of simplicity, then there's going to be a problem of under fitness. Your model, there's going to be under fitness. What do I mean by under fitness is that, the magnitude of the regression parameter will be unbiased. Will be biased. And of course, you are not able, you're actually going to underestimate the magnitude of contribution of the predictor variable to the response. And in a situation where you put a lot of regressors into your model, you could also run into a problem of over parameterization that we call over fitness. Now, this is a question. We find ourselves in a world where when I use few, my model may underfit. When I use more, my model will overfit. Then how do we stand in the middle? How do we balance the situation? And that is the focus today. In focus today, you're actually going to learn the criteria, the statistical criteria for identify important variables. We don't just include variables in our model. Okay, and that's what we call variable selection. Okay, so like I said, in my outline, I'm going to explain what we call model fitness and model complexity. Okay, then from there, I'm actually going to introduce you to 3 criteria for identify the best model. Then from there, we're also going to learn some method of subset selection, the stepwise regression. Then lastly today, bootstrap regression. So let's get started. Model complexity, model fitness. I'm going to start from model fitness. By model fitness, what are we trying to do? We actually want to see if there is an agreement between what happened in reality and what our model predicts. I'm going to say that again. Is there a discrepancy between what happened in reality? When I say what happened in reality, I'm talking about observed values of the response. And is there any difference between the observed values of the response and what our model predicts? Is there a gap? Then without you assessing your model, you actually want to investigate how well your model fits your data set. That's what we call model fitness. But let me tell you this. When I say model complexity, the model complexity is when I have more regressors in my model. The more regressors that I have in my model, the more my model becomes complex. I'm going to say that again. When you have more regressors in your model, or you have more explanatory variables in your model, okay, then I'm going to say we actually have what we call model complexity. But let me tell you this. The problem with the model complexity, the more you have more regressors in your model, then you're actually going to face with the problem of interpretability. You're going to be faced with this problem, interpretability. When your model is complex, you may not be able to interpret because you have a lot of variables. And that is what data scientists face. When a business person approach them to build a model with a high accuracy, okay, you know, the data scientists, the statistician, they struggle a lot with how to explain those particular variable, predictive variable that lead to high accuracy. Okay, so now when we are talking about, but let me tell you this is what we want to tolerate. We actually want situation where our model will feed the data well, and it's going to be relatively simple. We want to discourage having so many predictors in a model. Can we just get few ones? That would be also very important. That is our motive. That is what we want. Okay. Now, what I'm going to talk about now, if I want to talk about model fitness, if I want to talk about how my model actually fits the data set, what are the criteria for us to be able to know? Oh my God, we got two criteria that we use for model fitness: the residual sum of squared and the R-squared. The residual sum of squared is what we call unexplained variation. Unexplained variation. Okay, that is what we mean by RSS. Of course, if I want to know how wrong is my model, how good is my model in terms of model fitness, then a model with the smallest RSS should be a very good model. And a model with the highest values of the R-squared should be a very good model. But let me tell you this, when you are using RSS or R-squared, you don't put into consideration model complexity. You are only talking about the model fitness alone. I'm going to say that again. RSS, residual sum of squared, and R-squared, that we call coefficient of determination, they are criteria to measure model fitness alone. We don't use them for model complexity because they are not going to be appropriate for model complexity. Anywhere in the world, when you come across a research paper where they use RSS, residual sum of squared, and R-squared to decide on model complexity, that is totally wrong. Totally wrong. Because the RSS or the R-squared only talk about model fitness alone. Okay, well, let me tell you this. I put a dash. This could be a question in the midterm too. Dash, RSS means model fit the sample data better. That will be smaller. The smaller the value of RSS, I said RSS is unexplained variation. We always want to minimize unexplained variation. And you know what? The larger values of R-squared means the model fit the sample data better. Okay, but you know what? Here I'm just talking about model fitness. I'm not talking about model complexity. Okay, so take a look at that. Okay, excuse me. What determines the complexity in a model? When you have increase in the numbers of regressor, okay, then the more the model becomes complex. And that was why I said K, I'm using K here to represent the numbers of regressors. Okay, the numbers of regressors actually measures model complexity. Take a look at that. Okay, and you know what? What else a smaller number of regressor means? The smaller numbers of regressor actually means the model is very simpler. That's what it means. Okay, now Take a look at that. All regressors related to the same categorical variable, we count only once. For instance, when you have a categorical variable that has levels, okay, you don't count it based on the numbers of levels. You're going to count it as one. It's one categorical. For example, gender. Gender has two levels. I'm not going to say two regressors. I'm going to say one because the variable is just one. Only that it has levels. It's categorical. That's exactly what I'm trying to talk about there. Okay, I want you to say something now. I'm going to display some stuff. Take a look at this. This is a simple linear regression model, relatively good fit. Now, in a simple linear regression model, the number of regressors equal to 2. What are the regressors? In a simple linear regression model, take a look at this. This is a simple linear regression model. Regressors are 1 and x. 1 and x. 1, the coefficient of the intercept, x, the coefficient of the beta 1. Okay, so the k in a simple linear regression model equal to 2. A simple linear regression model has 2 regressors, but 1 predictor, x. That is a predictor. 1 predictor, 2 regressors. Now, when we feed the model, the RSS was 0.403. When I fit a model, k equal to 1 regressor, that's an intercept model, right? There's no x. What is the RSS? Okay, the RSS is 4.99. Compare 4.99 to 0.403. Of course, that one is better than that. Okay, simple linear regression model is better than intercept model. Intercept model does not have any predictor at all. Okay, now when I now compare that with a polynomial regression of degree 4, okay, polynomial regression of degree 4, okay, which is so complex, right? And when it is complex, k equal to 5, what is k? Numbers of regressors. Okay, in that, the numbers of regressors 1, x, s squared, s to the power 3, s to the power 4. Look at that. That is the 5 regressors that we talk about. K equal to 5. Now take a look at the residual sum of square. Residual sum of square equal to 0. Oh my God, situation where you have residual sum of square equal to 0, we don't want that. Because we know every statistical model must have a random component. And they can never give exact results. They should always be unexplained. Now, when RSS equal to 0, don't celebrate. You don't need to celebrate. Because when you are celebrating that's a problem of overfitness. When you have a lot of parameters in a model, when you have a lot of regressors in a model, okay, the model run into what we call the problem of complexity and overparameterization that will lead to overfitness. You can never trust that model. Now, what I just demonstrate to you now, as the number of regressors is going up, okay, what happened to the RSS? The RSS is going to be going down. Okay, now I want you to see, for instance, if we're looking at the effect of experience of professional workers on their salary, you fit a simple linear regression model. Of course, you can see a curve, right? You're going to say, oh, maybe that is not appropriate, because when you see a curve, then you're going to incorporate quadratic term. Now, but by the time you fit a simple linear regression model, look at the Rsquared, look at the RSS. Now, by the time you now fit quadratic, you see the RSS has gone down from 4789.046 to 111. And look at the Rsquared has increased because of the fact that you have incorporated what I call quadratic term. Now, when you decide to increase that further, look at that. So the polynomial of degree 3, you can see the RSS go down. The more you add regressors to model, the RSS is going to be going down and the R squared is going to be going up. But you know what? We can never trust them in this situation because theoretically speaking, when you increase the numbers of regressors, even if they don't make sense, the ROSS is going to go down, the R squared is going to go up. You cannot trust them. You know, and that is the reason why we say residual sum of square and the R squared they are not appropriate measures for model complexity. They're not going to be correct. Something needs to be done. I just demonstrate that to you right now. But you know what? If I want to consider, that was what I said, how did the ROSS change when we had more polynomial regressor? Of course, the ROSS is going to be going down. The R square is going to be going up. Okay, so take a look at that. But if I want to tell you, the best model here should be quadratic. You know why I say quadratic? In the sense that if you want to go from R squared for quadratic to that of cubic, the difference is not much pronounced. Look at that. It's 0.9247 and it's 0.9257. There's no, that just have a marginal difference. So you don't need to go higher. You can actually stop at quadratic. You get what I mean, right? Because when you continue to go, it's going to be increasing, but it's going to be a marginal increase. The increase is not going to be significant. You get what I mean, right? Okay, now, how did R squared change? You know, when we had more polynomial regressor, of course, it's going to be, R squared is going to be going up, okay? But it's not going to be a good measure. I told you, okay? Now, okay, go ahead. Yeah, if I heard you clearly, you said, am I going to stop when I notice, actually what happened is this. If you take a look at what we have right here, you notice a curve, right? Now, you see a very big jump in R squared from 0.67 to 0.92, right? You see a very big jump. So which means now when you now want to add more regressors, if you don't see a highly significant difference in the increase, like when you take a look at from 0.9247 to 0.9257, there is no significant increase. So therefore, I don't need cubic. I don't need polynomial of degree 3. I can actually stop at polynomial of degree 2 because when I keep adding, even though the R square is going to be going up, but there is not going to be a significant increase. Do you get what I mean, right? Okay. Now, the next thing that I actually want to talk about now, let's talk about the criteria for model selection. Now, you know what we now need? This is what we need as a researcher, as statistician, as data scientist, as machine learning expert. What we need is this. We don't need a measure that considered model fitness alone. We don't need that. Okay, when I say measures that consider model fitness alone, I'm talking about residual sum squared and R squared. We don't need them. You know what we need? We need criteria that put into consideration both model fitness and model complexity. That is what we need. I'm going to say that again. ROSS, R squared, they are only criteria for model fitness alone. But we don't need it. But you know what we need? We need criteria that put into consideration both model fitness and model complexity. That's what I want to talk about now. The criteria that consider them. No, these are the criteria that consider them. These are the criteria we should go for. Number one, adjusted R squared. Our R squared need to be adjusted in case of model complexity. If you really want to know how good a model is, when you have so many variables in your model, you don't use R squared as a measure. You just adjusted R squared. Okay, then we use the archaic information criteria that we call AIC and the Bayesian information criteria that we call BIC, a model with the highest value of the adjusted R squared is the best model. A model with the lowest value of either AIC or the lowest values of BIC is the best model. So I present to you criteria that actually puts into consideration model fitness and model complexity. These are the three of them. Okay, now let's take a look at the statistical architecture of adjusted R squared. If you want to compute adjusted R squared manually, what is the formula? Take a look at that. It is 1 minus RSS is residual sum of square. Okay, they are, divided by n minus k. N is a sample size, k is the numbers of regressors, and SST is sum of square total, which we call the total variation. There's something I wanted to pay attention to here. If you look at the formula of adjusted R squared, you are seeing what? There is a residual sum of square inside it. So which means getting our adjusted R squared, we are remodifying the residual sum of square. Don't forget, residual sum of square alone, we can only use that for model fitness. If I want to talk about model fitness and model complexity, then it means I actually need to modify the residual sum of square. And that's why you can see it in my formula now, residual sum of squared is still part of the formula for the adjusted R squared. So take a look at that. Now, I think this is just a question for you. As you increase k, when the number of regressors is going up, what happened to the sum of square SST? Don't forget, the numbers of regressors is k. So what happened to the SST? What happened to n minus 1? What happened to RSS? What happened to n minus k? So you can decide that using the formula. Now, another one is a K information criteria. That is the formula. Oh my God, look at something. The AIC here is also a function of residual sum of square. Look at that AIC. Look at RSS. So which means whether the adjusted R squared or AIC or BIC, we are remodifying the residual sum of square. Look at that. And the sample size, k, the numbers of regressors. Okay, now, so I just mentioned that. Okay, as you increase k, where the numbers of regressors is going up, what happened to RSS? Okay, when the number of regressors is going up, if you look at the formula now, okay, as the number of regressors is going up, what happened to RSS? Is it going to be increasing or decreasing or not changing? If you look at k, you can see that k is in a separate, right? The RSS is on its own. Does that, if I plug in whatever value for k, does it going to have effect on the RSS? It's not going to change. RSS is on its own. You see that? It's not going to change. And you know what? When you use RSS alone, when you increase the k, what happened? What do you see the other time? When you don't consider adjusted, when you increase the k, the number of regressors, what happened to RSS? It's going to be going down, right? But here, what happened in the AIC, when you increase k, does RSS going to go up? No, that is our intention. That's what we want. Okay, because k here, we actually want to make sure that we are not just adding variable. Now, what about 2k? When k is going up, what happened to 2k? Of course, the 2k is going to be going up. When k is going up, 2 times 2 is bigger than 2 times 1. So take a look at it. Okay. Now, we normally want to select model with the lowest AIC. Okay. When we have competing models, then the model with the lowest AIC is basically, and you know what? How do we compute AIC for model in R? This is the code. Maybe you run a regression. Probably you run a regression where you actually call a model. Okay, maybe you say model, okay, equal LM, maybe Y on X1, X2, and so on like that, probably up to SK. Now, if you want to see the result, you're going to say summary, model, right? Now, if you want to extract the AIC, if you want to get the AIC, you're just going to write extract AIC. Then you're going to say model. This will give you the AIC of the model. You know, or just say extract AIC model is going to return the value for you to see. Now, for the Bayesian information criterion, okay, the difference between this guy and the AIC, instead of 2K in the AIC, take a look at that. Instead of 2K here, instead of 2K, the BIC is represented by log of n. Look, you know, instead of 2, rather, instead of 2. 2, you know, 2, the AIC used 2, while the BIC, instead of 2, use log of the sample size. Look at the difference. Can you see that? That's just the difference. The left-hand side, if you look at n log RSS over n, you also have that in the AIC. You see that? N log RSS over n. Okay, it is the other part of the model that they are not the same. The other one is 2K. Why for the BIC? It's basically the 2 is represented by log n. Now the question now is, how do I extract how BIC in R? If I want to do that, I'm going to write extract AIC. You know, I'm working on BIC. I'm still going to say extract AIC. Then model name. Then I'm going to say K equal to log n. That is for BIC. Okay, but if I want to get the AIC, I'm just going to write this one. Or if I want to write this for the AIC, you know what I'm going to do? I'm going to say K equal to 2. That is the difference between them. For AIC, you know, my K is going to be equal to 2. For BIC, K equal to the log of n. Okay, now that's how to extract them. Okay, now let us, in an attempt to look at the effect of experience on the salary, we fitted different kind of models. Look at that. The first model is simple linear regression. 2 regressors, 1 and S, right? The second model, quadratic. The third model, polynomial of degree 3. The fourth model, polynomial of degree 4. You know, I told you the other time, if I want to compare these models, if you can't use RSS alone, and you cannot use R squared. I told you the R squared, the RSS, they are just for model fitness alone. Okay, now if I want to compare these models, then I'm going to use adjusted R squared, the AIC or the BIC. Now take a look at that. Now look at the AIC of each of the model, the BIC of each of the model, the adjusted R squared of each of the model. But let me tell you this, we can have situation where the 3 criteria, they may be conflicting. I'm going to say that again. We can have situation where the 3 criteria may be conflicting. Okay, it's just like somebody go to a court, okay, and they say, okay, if the person did not win, and the person now appeal in another court, there's possibility that he's going to win. He may win another court. At times there could be conflict in judgment. We can also have conflict among them. But when there is conflict, which one are we going to go with? It is mathematically proved and statistically observed that if there is conflict, we should go for AIC, the one said by the AIC. Okay, AIC, like if we take a look at this one now, what is the model with the smallest AIC? Then it is quadratic. Look at that. 299.2 is the lowest, looking at the AIC. And you know, I told you the other time that quadratic is good for that. Even when you look at the adjusted R squared, the highest values of the adjusted R squared correspond to cubic. Look at is 0.9241, which is a polynomial of degree 3. But when you look at the adjusted R squared of the polynomial of degree 3 and the polynomial of degree 2, there is a minimum distance between them. So why am I going for the more regressors? when there is marginal difference. You get what I mean, right? And that is the reason why here we're actually going to settle with the model suggested by the AIC. Anytime there is a conflict. Okay, if that is taken. Okay, we've talked about the criteria of model selection. Okay, you know the criteria now of model selection, but you know what? I want to walk you through selection method. There is a difference between the criteria of model selection and the selection method. Now I'm going to walk you through selection method now. When we're talking about selection method, we have all subset selection and the stepwise selection. Okay, I'm going to walk you through this now. Like I said, criteria is different from the method of selection. But you know what? If I want to use the method of selection, then I'm basically going to tell the world what kind of criteria am I using with the method of selection. I may want to use the method, a particular method of selection here, and I'm going to say, okay, the criteria I'm using is adjusted R-squared. I may want to use a particular method of selection here. I can tell the world the criteria that I'm using is a AIC or BIC. I just wanted to take note of that right now. Okay, let's get started. Now take a look at this. We have 3 predictors in our model, and the question now is, should we use all of them, or should we use a model with a fewer numbers of predictors? But in our model presently, we got 3 predictors. Let me tell you this. You know, if you don't consider any predictor at all, that is the second one, which we call the most simplest form of a model is intercept, right? Intercept model. If you look at the second one. Now, how many potential models are within that scope? And I'm going to tell you, if I, the numbers of models that you can actually have is basically going to be 2 raised to power p, okay, which is going to be 2 raised to power k minus 1. Like, for instance, how many predictors do I have right now? I got 3 predictors, right? Okay, which is going to be 2 raised to power 3. It means I'm going to consider 8 models. There's going to be 8 models competing, and it is only one of the 8 that is going to be the best at the end of the day. You know what? You know, this is a formula. I don't know whether some of you've heard about in mathematics. There's what we call power of a set. Power of a set. If I have a set S that have 1, 2, 3, and I want to talk about the power of this set, okay, it is 2 raised to power the cardinality of the set. What do I mean by cardinality? How many elements do I have? It's 2 raised to power 3, that is 8. Now, we want to apply the knowledge of mathematics into statistics right now. We got 3 predictors. And what is the possible numbers of models we can have? That will be 2 raised to power 3, which means 2 raised to power the numbers of predictors, or you say 2 raised to power the numbers of regressors minus 1. You know, how many regressors do we have now in that model? 4, right? So that will be 4 minus 1, 3, right? 2 raised to power 3, it means I'm going to have 8 models. Now let's look at the 8 models. Number 1, these are the 8 models now. 1, 2, 3, 4, 5, 6, 7, 8. These are the 8 possible models. The first one here, the intercept model. You know, in mathematics, if you have 1, 2, 3, and you want to find the power of a set, and remember then, the power of a set, which is a possible number of subsets you have in a set, you know, you can have 1, okay, 2, 3. Then this is when they appear once, right? When they appear twice, 2, 3, 1, 3, and when they appear all of them together, 1, 2, 3. Now, if you take a look at this now, 1, 2, 3, 4, 5, 6, 7, there's another thing. Empty sets, making 8. In statistical analysis, Empty set is the first one here, model without predictor. Do you get that? Okay, now these are the 8 models they're going to be computing, and we're going to choose one at the end of the day. Now, and that was why I said here, in general, we have k terms in the full model. How many potential models do we need to consider to find the best model? We have 8 models, 2 raised to the power 3, 8, right? Then how many potential models do we need to consider before we get the best model? Then I'm going to show you now. Now, this particular method that we want to use has a strength, because strength is going to go through all the possible model, but the weakness is it's going to be computationally expensive when k is large. Imagine if I have 10 predictors, that would be 2 raised to the power 10. That would be a lot of models, right? That is going to be the weakness. Now, let's get started. You're going to see something now. Now, this is the way it's going to work. We have what we call stepwise regression. We're going to decide, should we go backward? Should we go forward? Should we go both directions? What do I mean by backward? Okay, I'm going to start with all the predictors. Then I'm going to be going back, and I'm going to be eliminating predictor that is not significant. That's what we mean by backward. Backward elimination. I'm starting with a complicated model, then I'm going to be eliminating them out, one after the other, or one at a time. But when I say forward, with it forward, I'm going to start with no predictor at all. I'm going to start with an intercept model. I'm going to be moving forward. I'm going to be adding variable that is important. I'm going to continue to add until I get to the best model. And why the both direction, we have one that proceeds in both directions, but let me quickly walk you through this now. I want to start backward elimination. I want to start now. I want you to focus on the board. I want to explain the manual way to do that. Then I'm also going to walk you through how to do that now. You know what I'm going to do now? I want to start backward elimination using the AIC. We can talk about backward elimination using BIC. We can talk about backward elimination using adjusted Rsquared. But what I want to talk about now, backward elimination with AIC. If I want to start backward elimination, I'm going to start with a complicated model. You can see how many predictors? 3 predictors. Okay, that is the full model. I get the AIC. Okay, after getting the AIC, what is the next thing am I going to consider? In step 1, okay, that will lead to, at a start, I start with 3 predictors. Step 2, I need a combination of only 2 predictors in step 2, because I'm going backward. Now, take a look at this. What are the possible predictors if they want to appear in twos? X1, S2, X2, S3, X1, S3. That is my step 2. Then I'm going to get the AIC for each of them. Okay, you know what I'm going to do? I'm going to compare the AIC of the first step with the AIC of the second step. Okay, now I'm going to be looking for the AIC that will be smaller than the complicated model. Now take a look at it. Minus 110, minus 116, minus 119. Which one is smaller, more smaller than the AIC of the complicated? It is this guy here. It is minus 119. You agree with that? Okay, it means right now, up to step 1, the best model for now is basically model with just X1 and S3. Now, you know what I'm going to do? In the step 1, I'm considering 2 predictors, right? In step 2, I'm going to consider 1 predictor, 1. Okay. Now, and which one am I going to consider now? The one that I'm going to consider must have X1 and S3 in it. Take a look at that. Where does it come from? Because my current best model is the model that have S1 and S3, right? Then I'm going to break it down into 1-1 predictor, into the one that have S1 and the one that have S3. I'm not going to come here at all. This guy and the other guy, they are eliminated. We're not interested in them. You know why? Because their AIC is not smaller than -112. Even though I know -116 is smaller than -112, but there's another model. -119 is smaller than -116, and that's why I'm going to go with that. Now, you know what I want to do now? I'm looking for a model again in one predictor whose AIC will be smaller than the current best model. What is the current best model? -119, right? Okay, which one is smaller? Oh, -121, right? -121 is less than that. Now, my current best model is this guy here, the one with X3. Okay, now, after considering one predator, what will be the next step? The next step is going to be no predator at all. No predator. We want to see whether if I fit a model with no predator, I want to see whether the AIC is going to be less than that. Let's see. No predator at all. Step 3, no predator. When I find that, look at that, no predator. What was the AIC? Oh my God, the AIC is even bigger than that, the one with one predator. Therefore, the best model to fit is that guy here. Okay, take a look at that. That is the best model using backward elimination with the AIC. Now, the question now is, how many models do we go through before we arrive at the best model? Let's count them. 1, 2, 3, 4, 5, 6, 7. Before we arrive at the best model, we only go through 7. But you know what? What is the potential numbers of models in general for 3 predictors? Is 8, right? But we go through 7 before we arrive at the best. So what I'm trying to say now, using backward elimination with AIC, then that model is going to be the best. It's the one that we're going to run. This is what we call the backward elimination with AIC. Now, the next thing now, I quickly want to show you the forward selection. For the forward selection, you're going to start from the lowest, like from the model without predator, which is from the intercept. Look at that. That's where we're going to start. Forward selection. I'm starting from 0 and I'm going to be adding. But the backward, I'm starting from the complicated model. I'm going to be eliminating. Look at the difference between them. Now for the forward, I'm going to start with no predator, right? I get here, I see, right? The next step, I'm going to go to what? 1-1 predictor. 1-1. Okay? 1. Look at that. 1, 1, 1. Okay? Now I compute the AIC. Okay? Compare the AIC here with the AIC of the lowest, of the AIC of the intercept. Which one is smaller than that? Okay? They are all smaller than, they have the AIC that is smaller than that of the intercept, but we're looking for the most smallest. Which one is the most smallest? Oh, this guy here, -125. X2. Do you see that now? The next step, the step here is 1-1 predictor. Then the next step is going to be 2-2. Okay? 2-2 predictor. Okay? And you know what? The 2-2 predictor is basically going to come from here. Now, take a look at this. The 2-2 predictors that we're going to consider should be the one that have S2 in it. Why S2? Because right now, S2 is the current best model. If I'm looking at a combination of 2, okay, then I must consider S2 must be a component. Therefore, I'm going to have S2, S3, S2, S1. Can somebody tell me? Why is it that I don't have X1, S3? Can somebody tell me? Rsquared. Why is it that I don't consider this? Why is it that I don't consider? Okay, go ahead. Oh my God, good job, good job. Send a message to me for extra credit because right now the model with the lowest is X as X2 in need. So if I want to consider, the other pair, it should be the one that have S2 in it. And the only way we can do that, S2, S3, S2, S1. Okay, let's look at the two of them. Do you have anyone that is smaller than 125? No. Look at that. Minus 116, minus 110. Is there anyone that is smaller than minus 125? No. Therefore, we have to stop. We've already seen the best model. Now, I wanted to look at what we did in the stepwise, the forward and the backward. They actually arrive at different model. Look at that. When we did forward, the forward said considered model with S2. But when you look at the backward, the backward said consider model with X3. Look at that. There's a conflict between the forward selection and the backward elimination. There's a conflict. Look at that. Okay. And that is the reason, that is one of the disadvantages of a stepwise regression. And let me tell you this. You're actually going to see here the backward elimination. Okay. When we use the backward elimination, okay, it miss out the best model. How do I know the best model? A model that have the lowest AIC. When we're using the backward elimination, it did not even consider this guy at all. And that is one of the disadvantages of stepwise regression. There's possibility it could miss out on the best model. Okay, so take a look at that. Now, there's something I want to show you now. How do we do this in R? Oh, my time is up. You know what? I'm going to start from here on Wednesday. How you're going to do it in R? You can practice that. Every other thing, so I'm going to start from there on Wednesday. Okay, make sure you stay safe and have a very beautiful day.